I think everybody who's here is here. I'll begin with a word of prayer once I get up here. Then, Father, we thank you for this day. Again, I thank you for this class and just ask you to help us to use this time wisely just to prepare for the test, which is upcoming, Lord. In your name I pray, Lord Jesus. Amen. So, yeah, let's take a walk down memory lane. What did we do? It's been a while. Too much. That doesn't even make sense. So, we did study coordinate change and matrix congruence, the straightening theorem. We studied quotient space and solution sets as linear manifolds. You may not remember that as much, but it was there. Quotient space in the first isomorphism theorem, we definitely did that. Invariant subspace theory, like what happens when you've got a T invariant subspace, how does that look? Right? What are independent subspaces? We had that 5-part equivalence theorem that we proved. We introduced associative algebras. And so like there's a bonus project that will help you get stronger with that. If you've worked out some of that, that's good. I think probably working the first problem in the bonus project is probably wise for the test. So that's unfortunate because I haven't published solutions of it yet, right? So, but yeah, I'll try to say more about that in a second. Exterior algebra over a vector space. Talked about wedge products, how those calculate determinants, eigenvectors, diagonalization, of course, eigenspaces. More recently, we've discussed the Jordan form, how invariant subspaces, and we actually did this bit much earlier. We ended up covering this like way back up here somewhere. And then, of course, most recently we've been talking about the Jordan form, and then most recently, complexification, and then, of course, the differential equation. Now, the inner products and norms and Graham-Schmidt orthogonalization, this is not on test 2. Test 2 just covers my chapters 4, 5, and 7, or the textbooks for, I don't know, whatever it is. Anyway, the material since test 1, but not chapter 6. All right, so that's a brief overview. I have posted every single test I've pretty much ever given in this course in the most recent announcement, so there you go. That probably won't help you much, though, because this is a new course. It is fresh, so I'm trying to make fresh problems, but that does give you a sense of what I have tested before, and some of those problems are still good problems for you guys. Don't ask me which ones, because I don't remember, but I'll look back at them and figure it out. All right, so with that, you guys got questions? Feel free to ask them. I will say one thing I told, as a general point of order, like which proofs should you be ready to do? If I've spent a good amount of class time going over a proof, that's a proof I might put on the test. You know, like for example, the rank nullity theorem. Like we proved this in class. I discussed the proof of it 2 different ways. You know, the one is to use the fact that the coordinate maps are isomorphisms, and so like the null space of a matrix is isomorphic to the kernel of the map. The column space of the matrix is isomorphic to the image of the map. And so if you have a linear transformation from a finite dimensional vector space V to a finite dimensional vector space W, then you can look at the matrix of it, which then is going to be a, you know, m by n dimensional matrix. And we already know from 221 that we have pivot columns and non-pivot columns, right? And the number of pivot columns is the dimension of the column space, and the number of non-pivot columns is the dimension of the null space, which we call the nullity, right? And on the other hand, the dimension is preserved in an isomorphism, right? So the dimension of the null space is the dimension of the kernel, the dimension of the column space is the dimension of the image, and as such, you know, number of vectors in the matrix, number of columns in the matrix is equal to the dimension of the column space plus the dimension of the null space, which is equal to the dimension of the kernel plus the dimension of the image. But on the other hand, the number of columns is also the number of things in the basis for your domain of the transformation, right? So that is dimension of V is dimension of the kernel plus the dimension of the image. That's the rank nullity theorem. that was one proof that I gave in here. And I might have never, I just talked through it probably just like I just did. But that is one way you could prove it, right? The other way you could prove it, of course, is by a direct, like, linear algebraic argument, and we did that as well. We started with a basis for the kernel. We extended that basis to a basis for the whole space. We then argued that the vectors which were not in the kernel had images which formed a spanning set for the range. We then argued that it was necessarily a linearly independent spanning set for the range, and as such, we have number of things in the kernel, number of things not in the kernel basis is equal to the number of things in the whole basis for V, but that is actually, again, the dimension of the kernel plus the dimension of the image is equal to the dimension of V. So we have, these are very different proofs, right? So the second proof is the linear algebraic proof. This first proof is really just stealing the result from matrix theory, which is fine. So, you know, anyway, so that's an example of a proof I might ask you in here. Can you guys think of any other things I might ask you to prove? You're like, we're not going to answer that question. We're not born yesterday. Nice try. Right?
Was that yesterday?
What's that?
What about yesterday?
Not born yesterday. I'm not going to answer that question, right? Let's see here. How? Which one? Zorn's lemma. You can't prove Zorn's lemma. That's funny. How about this one? Right? We spent like a day and a half of class on this thing. You know? So I wouldn't ask, but I obviously wouldn't ask you to prove the whole thing. But might I ask you to prove like one of the implications in here? Like, that's a potential test question because I went through these arguments pretty slowly and methodically for the most part, in as much as I'm capable. So, you know, that might be another thing I might ask you. How about just the characterizations of, you know, let's see here. You know, so I usually can test the first isomorphism theorem just by asking you to apply it. That's usually sufficiently challenging for that, you know, because there's something really new about that, isn't there? I'm always looking for some good questions to probe whether or not you understand quotient space. I already kind of betrayed myself and gave you a really good example of that kind of question on the quiz, right? The one that you guys couldn't get the first time, and then I gave you like a week and some more to think about it. Sorry, I don't have those graded yet. I will grade those this weekend. If you want to pick it up earlier Monday before you take the test, you can. Okay? So, I'm sorry, I got distracted. I was recently informed I'm moving to the Spranex. Yes, oh indeed. I have personally advocated that the Mountain of Dew be moved to the top of Sprano's office, to tower over him, if you can envision that. Yes, you know what I'm talking about, right? You know, yeah, the Mountain of Dew. Put it on top of his bulletin board roof. That's what we're going to do. It's very exciting. So yeah, I'm moving, I guess. Maybe this weekend, I don't know. I also think just very simple questions about like what geometrically the quotient space looks like are also like very nice low-level questions that gives me an insight as to whether or not you understand what's going on. Those aren't that hard if you understand what the coset is. That's really kind of the first thing, is understand what the coset is, you know? What is it? What is a coset? A subspace is essentially like some kind of plane or hyperplane through the origin in the abstract vector space, right? X plus W is just a parallel shift of that. It's just a shift of the plane up off the origin. So these are literally just shifts of the, you know, the subspace. What I was talking about with the solution set, I don't know if we ever quite got to it in class, but it's not much, right? If you have a solution, if you have a listen to me, if you have a linear equation, AX equals to B, right? what does the solution look like? Well, the solution looks like x is equal to xh plus xp, where h is the homogeneous solution and p is the particular solution. See, where axp is equal to b and axh is equal to 0. So this means that xh is an element of the null space of A, right? It's in the null space of A, and that means that x is an element of xp plus the null space of A. You see? In other words, the general solution to a non-homogeneous problem is a coset. It's a coset, it's a parallel translate of the null space of the matrix. Different particular solution gives you different coset. But they all share the same homogeneous piece, you know? So I don't know. I think that's an interesting application of the concept of coset, circling back to 221 stuff, you know? So I don't think I ever quite came out and said that in here for you guys before. I'm sorry about that. I need to create some more homework problems which kind of get you guys to discover that for yourself. I don't think I have that homework problem yet. Could you guys explain to me why V mod W is a vector space over F? Like, what's the most critical issue here? It's before this in the notes, right? But the critical issue is that this equals to that is unambiguous, right? That if I was to choose a different representative, right, like x prime plus w is equal to x plus w, and y prime plus w is equal to y plus w, that when I add x prime and y prime, it's equal to the same coset as x plus y plus w. That's the big issue, which was also the issue in why that, function, quote unquote, I gave you wasn't really a function without extra information, right? Without the t invariance of the subspace, which I'm going to write up a solution for you guys. You don't have to wait for the solution. I'm writing a solution to the problem I assigned because I know not everybody got it quite right. So I will write a solution for that and hopefully have it posted tonight if all goes well. So what I'm trying to say is really this proposition right here this is something I would study if I were you. I mean, I would make sure I could prove this. I can easily, a lot of times I'll just ask for like half of the proof, right? Like one part of the implication. So don't just memorize it. You need to understand which part you're doing. You know what I mean? Sometimes people just memorize the whole thing, and if I ask half the question, they still give me the whole answer. This does not inspire, I mean, yes, I wish I had your memory, but I desire your understanding. So anyway, this business here obviously is not test worthy, all right? This was just a quirky calculation. On the flip side, if we look at, you like that part? Oh, you didn't like that part. Okay, well. Or where was I? Oh, come on. Let's see here. So you guys can jump in anytime. Let's see here. That's a super friendly test question, isn't it? That's really a test 1 question, isn't it? You know? But some of you would like to redeem yourself from test 1. Maybe I'll give you a chance, you know? How about this one here? You know, it's been a little bit since we thought about this, but intersections of subspaces require some thinking, right? So as a general point of order, if you didn't have time to solve a particular problem, you really should look at my solution and try to understand it before the test, you know? Because I usually make tests which are born of the homework problems I've given students. So this problem here didn't require technology, right? And this actually just follows the proof of the straightening theorem. So I think that's a nice problem. It's actually not, that I could put something like that on the test. It might not be exactly like that, but It's also kind of annoying to put that problem on the test because there's a certain ambiguity in part of it, which makes it really hard to grade. So that is working against it being on the test, but as I'm lazy. Do you guys understand coordinate change? I hope. I personally always fall back on those diagrams I drew for you guys, but make sure you know like the really basic column vector change stuff, right? Like for column vectors, if we want the coordinate of x, we just do what? We do the inverse matrix times x, right? Like that. And the coordinate transformation for t beta beta, we can also get by what? How's it go? Is it beta inverse? See, I'm rusty. I have to look this up, but it might be that. My bad, that's kind of dumb. Let's make this the standard matrix. There we go. But these are only good for what? What's the context? Fine. Context there is, linear transformation on columns, right? So if I have an abstract linear transformation, the rule is not quite this. It's more interesting, yeah. All right. So any questions about all this? Now that you look, yeah.
I was looking through the solution of that thing, and I didn't quite understand the solution of the last problem.
Which mission or quiz or
That.
this particular one?
Yeah.
Okay, so as you guys look back at this, what are these?
Eigenvectors.
Yeah, this is eigenvector. This is a typo, and that's an eigenvector. This was obviously supposed to be V2 here. I was trying to make it, Anyway, sorry. So you wanted to know about like problem 42?
No, past that.
43?
I think it might have started with problem 45.
45? All right, let's look at 45. Let's see here. So we're given the transformation's a second derivative operator, and we're trying to induce t bar on the quotient space of the kernel in that way, right? So I think that's essentially what the first isomorphism theorem does, right? Like we mod by the kernel and define the map by the transformation on the representative of the kernel. Like this is the first isomorphism theorem construction. But so I can just go through, but is there a particular place that it stops making sense, or?
Yeah, I don't remember where it was.
Oh, okay, we'll just kind of go then. So we have a linear transformation, and so this is the composite of a linear transformation within linear transformation, which is, again, a linear transformation. And the kernel is the set of things that have second derivative 0, which of course is linear polynomials, right? Integrate twice. And this is just integrating twice is all this formula is, right? Of course, you can check that if you differentiate this twice, the p plus 1, the p plus 2 cancel, and it leaves you that. Oh, yeah, right there. I guess I did check it. Well, that's good. Don't have to take points off my solution. Thus, t maps onto the monomial basis for r of x, right? Because I have taken an arbitrary power p and showed you that I can attain it as the image of that, right? So that means that t is a surjection, which means that the t bar defined on the quotient is a surjection, which then means the first isomorphism theorem applies, and r of x mod the kernel is the image of t, which we just proved is r of x. So that means it's an isomorphism, which, among other things, means that it has an inverse. Come on, people. And then, well, the formula for the inverse is just twice integrating is all it is. And that's, the constants of integration, ordinarily, if I was just working with polynomials and not quotient spaces, that wouldn't be an honest formula, right? Because I'd be adding a constant. That's not one thing, it's a whole class of things if I have to make an arbitrary constant, right? But here, we're working with equivalence classes, you know. We're modding by the kernel, which means we're setting arbitrary copies of a linear polynomial. They're being treated as 0 in the quotient, right? So that makes this, you know, I just set the constants to be 0 basically and took that particular antiderivative as a representative for the coset there. So.
How you use the isomorphism theorem. So did you use it to prove that the real polynomial non-kernel is isomorphic to a real polynomial? Is that what you did?
Well, the construction of the first isomorphism theorem is that the T bar constructed in this way is an isomorphism onto the image of T. So because the image of T is all polynomials, that's why I have an isomorphism.
So you were just proving that the first isomorphism theorem.
I'm using, essentially the only thing really to prove here is that the map is surjective, and that we're also asked for the formula. But yeah, the fact that it's an isomorphism really is from the first isomorphism theorem. Again, it is the construction. This is the construction of the first isomorphism theorem. So that's how I know that T bar is an isomorphism. I mean, I could prove it too. I mean, we could take, you know, two inputs that are possibly, you know, just we could assume like T of one input equal to T of another input, and prove that those two inputs are equal. Prove it's 1-to-1. You know, we've proved it's onto in the solution. Yeah.
Well, you did do that without the inverse.
Yeah, this is okay. This is also true. Since the inverse, since I give you a formula for the inverse, I guess that does also prove injectivity. But fair enough. But was there another one, or
Yeah, there were other problems.
like the next one, or
Yeah, I think the rest of the problems.
just the rest of the problems? Okay, sure, we can look at them. So this one here, what were we doing? It's been a minute. We had subspaces of V. We're given that the sum of the subspaces is, well, I just said, well, okay, so the sum of the subspaces is a subspace of V. And notice also that the subspaces themselves are subsets of the sum, right? Which is clear because we can put that to 0 or that to 0, which shows you that those are subsets of the sum. All right. If we have alpha in the annihilator of the sum of the subspaces, that means alpha of x is 0 for all x in the sum of the subspaces. But since W1 is a subset of that, that means that alpha annihilates everything in W1. And since W2 is a subset of that, that means alpha annihilates everything in W2. Which is to say that alpha is in the annihilator of W1 and alpha is in the annihilator of W2, which is to say that it's in the intersection of the annihilators. Consequently, if I pick alpha in here, it's also in here, which shows you that the annihilator of the sum is a subset of the intersection of the annihilators. I think that direction of this problem wasn't too bad. I don't remember. Well, at some point, these problems get ugly. Maybe this isn't that problem, though. On the flip side, if I pick beta in the intersection of the annihilators, then that means that beta annihilates everything in W1 and beta annihilates everything in W2, right? If I pick x in the sum, then that means that x can be written as x1 plus x2, where x1 is in W1 and x2 is in W2, which means that if I look at beta of x, by linearity of beta, that's beta of x1 plus beta of x2, but by assumption, that's 0 and 0 because it's the annihilator of W1 and W2. Which then shows you that but x was arbitrary, so we've just shown that beta is an annihilator of W1 plus W2, which then shows you that this is a subset of that, so they're equal. This is not the one you had a question about, is it?
It was, but I think
Okay, good. At some point, I got stumped. This one didn't stump me first time through. Maybe this one. This one might have stumped me. Suppose the dimension of V is finite and V is, so what does this mean? Here's something you guys, everybody should know. What does this mean? This mean, but what does it mean?
Their intersection is 0 and they span V.
Right, so exactly, so W1 intersect W2 is 0, and W1 plus W2 is equal to V. That's what it means for two things. Now if you have three things, it's more complicated, right? For three subspaces to be the direct sum, we need that the intersection of W1 plus W2 with W1 plus W2 parentheses with W3 is 0. The intersection of W1 plus W3 parentheses, W1 plus W3 parentheses intersect W2 is 0. W2 plus W3 parentheses intersect W1 is 0. So you need the intersection of the sum of the other two with the remaining one in all possible ways to be 0. And you also need the sum of W1 plus W2 plus W3 to be V. This is what I was talking about in that 5-part proof thing. Like part of that is the definition of invariant subspaces, not invariant subspaces, independent subspaces. I'm describing the independence of three subspaces. All right, let's get back to this problem here, right? So we have V as the direct sum of W1, W2. And we're going to pick alpha. We're trying to show that this is equal. All right. So I start with this containment. I try to prove that this is a subset of that. All right. So alpha's in the sum, the intersection of the two annihilators. All right. So that means that alpha kills vectors that are either from 1 or 2, W1 or W2. Great. Now, if X is an element of V, then that means that there exists, in fact, I could put an exclamation point here because there's a unique X1 and a unique X2 such that X1 plus X2 equals to X. The uniqueness doesn't really matter to us here, but anyway, I'm just saying technically they're unique. And as such, when I take alpha of X, I've got this plus that, which is alpha of X1 plus alpha of X2 by linearity. But this is 0 and 0, so we get 0. Lo and behold, which X was this in V? Oh, that's right, any X in V it kills. Therefore, it's in the annihilator. Well, therefore, what? If alpha of X kills every X in V, that makes alpha not just any dual vector, but the 0 dual vector, because it kills every single vector. So alpha is equal to 0, which shows you that if we pick something that's in the intersection of the annihilators, it's just the 0 vector, the 0 dual vector. So that shows me that the intersection of annihilator 1 and annihilator 2 is 0. It still remains to show that the sum of the annihilators is V dual. All right. I had to use a basis argument here. If you found a coordinate, an argument without basis, then great, but I don't know it. I don't think I've seen an argument without basis for any of you guys. Anyway, so if I have basis beta 1 for W, basis beta 2 for W2, like so and like so, all right. Now, of course, N1 plus N2 has to be N, right? Dimension W1 plus dimension W2 is N. And then I define dual bases. So these are the bases which give you Kronecker delta ij like this. So this is from 1 to N1, and this is from 1 to N2. And then, technically speaking, those are only defined to start with on just W1 and W2 respective, but I extend them to the entirety of the vector space, as is my, I'm free to do that. So, like I said here, technically this and that, but I'm going to extend them to the totality of the vector space by just saying they're 0 outside where they're non-zero, right? So I define extending the dual bases like this. The rules are simply that Fi acting on a Gj is 0 and Gj acting on an Fi is 0. So the only way the dual bases here are non-zero is if they're acting on their own kind, all right? So, all right. Then once I have that all set up, I can't decide whether it's capital or lowercase an. So the F upper I are in the annihilator of W2, and the G upper J are in the annihilator W1. Why is that? It's because F upper I, by construction, kills all of the G1, all of the G sub i's. If you kill the whole basis, you've killed an arbitrary vector because the annihilator, the dual vectors are linear. So if you know, whenever you have a linear transformation, if you kill the basis, if you send the basis to 0, that means the transformation 0, right? So the fact that I know that this is true implies that. The fact that I know this is true implies this. Because the FIs form the basis for W1. So if they kill everything in the basis, then it follows that they annihilate everything. So admittedly, I'm missing a line here, okay? My bad. Take away my points. All right, so, or did I have the proof down here? Oh, I have the proof down here. Well, okay, fine. I guess this, I'm saying this, and here's the truth. Here's the claim, the proof of the claim, all right? Fi acting on that is x2 is a sum over the gj's of cj, but this is by construction 0. All right, great. And likewise, if my x1 is built from the basis of w1, means it's built from the fi's, and then but by construction this is 0. So, all right, great. So what this all means is that the dual basis for the first space is a subset of the annihilator for the second space, and it means that the dual basis for the second space is a subset of the annihilator for the first space, right? Which you have a fuzzy feeling has something to do with the inner products and the orthogonal complements we're studying right now. It's a good feeling. It's a correct feeling. We'll make that more precise, but not on this test, I promise. Okay. That's something I'd have to bring out on the final, because that's when we have all of the pieces to play with. But anyway. Okay, so anyway, what that means then is n1 is less than or equal to this dimension, and n2 is less than or equal to that dimension, right? Because if these are subsets of those spaces, that means this is a linearly independent subset, that's a linearly independent subset. As such, that means that the dimension of the annihilator of W2 cannot be less than n1, and this cannot be less than n2. But we also know that the dimension of the annihilator of W1 plus the dimension of annihilator 2 is equal to what? Well, we happen to know that there's a theorem which says that if you have the dimension of a sum, it's, do I need to write this out? Do you guys know what I'm referencing? Maybe no one knows what I'm referencing here. I'm talking about the, Hey, at least you're not responsible for the proof of this theorem because I didn't do it in class, right? Be happy. I didn't. So like this one, the sum of W1 and W2 is equal to the dimension of W1 plus the dimension of W2 minus the dimension of the intersection of W1 and W2. That is proved in the notes. It takes me about a solid half hour of class to prove that. It's not that easy to prove. But you guys are safe. I didn't prove that in class, so I wouldn't ask that of you, right? I have asked linear algebra to prove that before at some point, I think. You guys could probably figure out when. I think I gave you all my tests. But so I'm using this here. See, this is this subspace plus that subspace is the dimension. So like this dimension of the sum of the subspaces is the dimension of the one plus the dimension of the other minus the dimension of the intersection. But here the intersection is what? 0, right? So we already know that this is 0. And we know that this has to be at least n1, and that has to be at least n2. But what's the maximum dimension this can have? It is a subset of V dual, which remember has the same dimension as V, right? There's something you ought to be able to prove. Prove that a vector space is isomorphic to its dual space. Can you do that? How would you do that? So notice that this, oh man, what happened here? Oh yeah, it's a plus. I was reading it tan. So the sum of annihilator of 1 and 2 is a subset of V dual, which means that the dimension of a subspace can't be more than the dimension of the whole thing, right? But this is at least, anyway, so that forces the dimension of annihilator of 1 and annihilator 2 to be respectively n2 and n1. Which then gives me that the sum of the annihilators is the dual space, which then completes that proof. So, yeah.
When you use dichroic, is that a natural property of just annihilators, or is that something constructed something?
That is the definition of dual basis. So, That's what happened? Oh, yeah, yeah. Mountain Dew in the trash can. I was at the math meeting earlier today, and I looked over, and then I looked at the person sitting behind me, and I was like, how long does he think this meeting's going to be? He had 4 Mountain Dews in front of him. 4 Mountain Dews. It was an hour. I mean, it was an hour and a half meeting, I guess. He said he was into his 3rd one at the end of the meeting. I respect it, but no, this is the definition of dual basis. So when we say that the basis for the dual space is dual to the basis of the space, it is by construction the linear transformations on the vector space, which are 1 when they hit the vector that they're dual to, and they're 0 otherwise. But that defines the linear transformation on the whole vector space because you've defined the values on a basis. And then by the unique linear extension theorem, there's a unique dual vector. So it's the definition of dual basis. Now I did something a little bit more than that because I extended them past, like I'm defining them to be the dual basis for just W1. But then I'm extending it to the rest of the, it's in some sense it's just this question of notation using the F and the G here. You could do this problem with just using like indices and keeping track of which part is which. I just think it's easier to follow the argument if I use different letters for the basis for the different subspaces is all. But anyway. So we really should go to the other, we're spending all of our time on this one. I don't know, we should continue this, but so here we have the transpose of the map. How did we define that? So by definition, the transpose is a mapping from the dual space to the dual space. Generally, it would be in the opposite order, but it's hard to see the contrast of V and V. So yeah. So T transpose acting on alpha of X is alpha T of X. That's the definition of the transpose. But anyway, I don't really want to talk about this problem right now, unless there's a question. Like, yeah, I don't know. I mean, let me see. Is there a particular thing in here that was vexing, or? I mean, it took me a while to think through this problem, as I recall. So, let's see here. So I think you guys did well on this quiz, right? No? Am I too far away from it? I've forgotten what happened. But let's look back at it and see why it should have been easy. How about that? Right? So W1 what was I talking about earlier today? What was it? I can't remember. X2 oh man, I meant to white that out. Look at that. X22. So x squared, x cubed. The point is, this generating set is always a subset of the span. All right? So that means 1 and x are in W1 and x squared and x cubed are in W2. And so if I add them, that means all of these are in W1 plus W2, but that clearly implies that this must be P3. If you've got the monomial basis inside your subspace is the whole thing. All right. And the intersection is 0. Why? Well, if you had, a linear combination of 1 and x squared and x cubed, if they were equal, by equating coefficients, you get a, b, c, and d all 0. So, yay. So this was not a hard problem. And I would like some questions like this on your test. Not this question exactly, but questions like it would be good for me to ascertain whether or not you understand direct sum, right? Intersection of subspaces, span, linear independence, these things matter. I've been trying to do induction examples in here. This was that. I think you guys got this one. Let me not go on here. I know not all of you are where you need to be yet on the determinant stuff. So if you know you're weak on that, then I would encourage you to fix it. The bottom line, there's really, maybe there's really just two things that we really learned overall. The one is that to calculate the determinant of a matrix with the wedge product, what we do is we take the wedge product of the columns of the matrix, right? That has to work out to a number times the wedge product of the standard basis. That number defines the determinant. That was our wedge product definition of the determinant. The other thing, which is just super useful, is that if you have vectors and you wedge them, if they're non-zero, they're linearly independent. And if the wedge is 0, they're linearly dependent. That's so nice, isn't it? Like as a calculational principle. So this one here, when I take, of course, when we have symbolic stuff, it gets more challenging, but when I took this, I got this star as my wedge. And so what happens, of course, is that this forces D to be 0, because ultimately these three forms, they're all independent because they don't have any common index, you know. Well, they don't have the same distinct triple of indices, I should say. Like 4, 1, 2, 4, 1, 3, 4, 3, 2. There's no way to combine these, all right? On the other hand, these guys are all 1, 2, 3. Just, you know, so like rewriting it, I get minus A minus B plus C times that wedge. And so I must have D equal to 0, and I must have, you know, A minus B plus C equal to 0. If I do want the wedge product to work out to 0, which is what I would need in order for there to be a linear dependence between V and V1 and V2, which is what it means for V to be in the span, right? It means that V is linearly dependent on V1 and V2. And I'll write the solution for problem 4 here eventually, hopefully tonight. Any questions? Oh, we won't do that to you. This is actually wrong. This solution's wrong. Nobody told me. Students. Although the kid in my class today figured out it was wrong, and we fixed it, so it's good. It was good. So, in terms of the Jordan basis stuff, you know, you need to know what to do with the Jordan basis if I give it to you, right? Like interpretation, like, you know, make sure you know the definition of like the K-chain, the real Jordan form, I probably ask us a question about like how to solve a differential equation, because I think you guys can do that. Or at least you should be able to do that. And I also found these calculations really fun. I don't know about you guys, but this T-cyclic stuff, like this was a very interesting calculation, don't you think? I really liked this problem. It was interesting, like the way you had to think through it and everything. This one here wasn't bad, but you do need to know some bells and whistles about the determinant, like the determinant of the direct sum is the product of the determinants direct summed. That's one thing. And also just this theorem that we had about like our big theorem about invariant subspaces, right? If you have independent invariant subspaces and their direct sum forms the whole vector space, if you have a T invariant map with respect to that decomposition, then the matrix of the map is simply a direct sum of the blocks. You know, it's a direct sum of the transformations formed by just restricting to just those subspaces, right? That was our big theorem about independent invariant subspaces. And so once you have that theorem, and you have the inductive extension of your other homework problem, then it's immediate. This problem's pretty much immediate. Let's see here, what else should I tell you about? Well, I don't want to say too much more. I'll just say that, like, it would be good for me to ask you questions about like minimal polynomials, possible Jordan forms, and there are lots of like simple logical questions we can think about, right? Like I was talking to Samuel earlier. Which problem were we talking about? I liked the conversation we had. It was good. This one. So this problem. I was thinking about this. There's something interesting here. So we were asked to find the Jordan canonical basis for this thing, right? So first order of business, I just calculated t acting on sort of the natural basis. And when you look at that, you should see what you're looking at. You should see, oh, this is an eigenvector. That's an eigenvector, right? You maybe even should see that this is a generalized eigenvector of order 2, because this gives you back at itself plus the previous thing. So this means eigenvalue 1. You're looking at t minus 1 times t e to the t is equal to e to the t. Now it breaks down here, right? It's almost a generalized eigenvector of order 3 as it stands, but there's this pesky 2 right here, right? Fine. So that's one thing. It's just like recognize what you're looking at for one thing. But what I did was just to calculate the matrix and then work things out. And so the thing is, once you find that you have eigenvalue 1 3-peated, right? And once you find that the eigenspace is one-dimensional, you already know it's a 3-chain. It's inescapable. You can't have anything but one 3-chain because otherwise you'd need additional eigenvectors of eigenvalue 1. So even without calculating this and that, I know that the Jordan form has to look like J3 direct sum J2, even without all this calculation. Now with this calculation, I can do more, right? I can actually construct the basis. Now I have a half here because I've got this in here. Notice that you can multiply this by anything and it's still a Jordan 3-chain with eigenvalue 1. I can multiply this by 42. I'd have 42 e to the t, 42t e to the t, 21 t squared e to the t. That would be a 3-chain with eigenvalue 1. You can multiply the chains by whatever you like. As I've told a couple of you, once you fix the top of the chain or the bottom of the chain, the rest is put in place. Right? Once you pick a specific vector to be the first thing or the last thing, the rest has to fall in line with that choice of scale. Same story about this other one. See, I got these pages out of order, guys. Watch out for this. I'm sorry. So like page 10 comes before page 9. Don't be confused by that. Yeah, sorry. I mean, there is a 5D continued on the previous page. That was kind of a clue. But so if I don't have a direct sense about what the eigenvectors are, I just calculate the matrix, right, with respect to the usual basis. And in this one, so many of these examples, the matrix has just been triangular, so I can read off the eigenvalues. I think you guys all know about that. Nobody in here is going to get a triangular matrix and then go to the trouble of like expanding a determinant, right? You're going to be like, no, down the diagonal, right? But this one here wasn't, so I actually had to calculate. And I saw this, which gave me this. And so my eigenvalue 2 is 3-peated and 4 is 1. And again, once I show that the eigenspace with eigenvalue 2 is one-dimensional, it follows that I must have a 3-chain there. If I had found that the eigenspace of eigenvalue 1 was 2-dimensional, it necessarily implies I have a 2-chain and a 1-chain. Because the net dimension of the generalized eigenspace of eigenvalue 1 is 3 in this problem. Because remember, the algebraic multiplicity reflects the dimension of the generalized eigenspace. Oops. So what I'm saying here is actually once I do this calculation and find out, oh, there's only one eigenvector. And by the way, notice how I'm doing eigenvector calculations. Notice how little I write. You also can do this if you understand. See what I do? I write this, I write that, I look at it, I go, oh, so this means that the third component's 0. Once I know the third component's 0, this tells me the second component's 0. If I know that the second and the third component, second and third component 0, that makes the fourth component 0. And there's nothing on the first one, right? So I could just look at this and think and see that the eigenvector is just that. I don't need to work out the row reductions if I don't want to. You are also free to think. Anyway, so lo and behold, what I'm trying to say is, actually, once I find out the eigenspace is one-dimensional, I could write this down immediately if I wasn't burdened with the problem of what has been. Hopefully we all won't be soon. But, sorry, that was a little Trump joke right there. But so this right here, I need to actually do the calculations to find the basis. But if I didn't have to, I could write this down without all that calculation. I'm just pointing out. Anyway, I guess that's all I got for you guys. So just do your best. If you've done the homework, you should be prepared. I'll try not to make the test too long,